So I'm going to talk about a tool to study sensitivity of Geant4 prediction to the variation of a physics model parameter. So this is the joint effort of the hadronic group inside the Geant4 the collaborations. So unfortunately, I'm not actually one of them. And all right, but I try to convey, the best I can. So the Geant4 is the leading detector simulation in contemporary, the high energy physics simulation. Also, not only in the HAP, but also its application domain is rather wide, including space science and medical and biology and so on. So it employs a set of validation physics model that span the wide range of interaction the energies. For example, here showing is the set of all hadronic physics model inside the Geant4 over the wide range of the energies. So for each of these boxes, actually basically span the relevant energy region there. And also each Geant4 physics model rely on either the measured cross section or some theoretical models which involve the many physically motivated parameters, and also tuned to cover a wide range of possible experiments. So not only focus on the one specific physics process, but try to be more general. And so this basically will have cover the different particles, and also you have no way to actually tune all different models out there. So in some sense, Geant4 is a toolkit. It's not try to pitch your actually specific models. So that at the present moment, there is the hadronic model. The standard one is a the combination of a Fritjof and the Bettini cascade and free compound. Has around 40 configurable parameters and 17 switches. And the Geant4 collaboration like to add more parameters that can be configurable in the future. So the question is the how sensitive Geant4 prediction to the variation of a model parameter, and also what uncertainty associated with the physics model or group of a model. So which is involved in the simulation, either in the physics analysis or detector design and so on. So the relevant the things you should address is what is the validity range of a parameter, and also some cases the certain parameters are strongly correlated, so you cannot really change it one thing with a blind way. And so the work is basically motivated by the Geant4 user communities, and the Geant4 collaboration start to investigate this. Also, the simulation usually do not give these systematic errors, because usually you quote the statistical or in simulation the point. So, but this is open up there's some possibility you can add actually the systematic based the rooted in the physics model itself. So the toolkit features the framework is based on the ACAT framework, which is the common software layer to store and access scientific data and to schedule algorithm in the efficient and convenient way. So this is something you can think of as something similar to the CMSXW. Core is basically the multi-variant analysis, and also you can do the collective analysis for different model parameters at the same time. And also you can talk to dossier repository. This is the database of scientific simulation and the experimental research. So the containing the measured experimental data or the simulation the result. Basically, right now is the majority of Geant4, but in the future will include the simulation by Geant or the other cases. And so this is a sort of a simple workflow and also a component of the analysis. So it's pretty much following standard CAP analysis within the big framework. So starting with the configurable the geometry, and then you basically setting the what parameter you like to change, and then put it in the either full simulation or process level single particle interactions, and then do the bookkeeping and put the output, then do the either the analysis one by one, or you can collect the different analysis for multivariate analysis, and then you can break this the couple of steps for your convenience. And so the current simulation can handle of course one the parameter, or also multi-parameter cases, and it's divided basically 100 points in the allowed sort of guess the range of valid reason, and then it do basically the multivariate analysis, and the relevant question the Geant4 developer tried to answer is how much Geant4 prediction vary with one or another parameter. Also, because before they open up the possibility to vary, they need to understand this first. And also, what setting of a model parameter bring the Monte Carlo closer to the data, and can we narrow at least quantitatively the validity range of parameters. So still this is developing the project, and the result I'm going to show is based on the chi-square as a function of parameter values, and this is chi-square is basically the difference between user sense data and Monte Carlo in this case. So the first example is the longitudinal profile. This is basically average energy deposition along the G position in the liquid argon detector shooting the 2 GeV pions. So in this case is basically Bettini cover below 10 GeV. So the relevant parameter is the Bettini radius scale, and cross-section scale actually vary quite largely here. Just try to illustrate this is default, and this is the sort of the maximum variation changing the scale from the default values. So this is sort of one example, and the next example is the multivariate analysis. So here is the secondary proton or pion production shooting the proton beams to the laser target. So showing here is basically the cross-section scale versus the radius scale, and this is a combined chi-square. So the point here is when you look up to this combined value, if you try to find the minimum, so that sometimes doesn't necessarily equivalent to the best value of each of parameters. So the complication comes in, and so next example is the shooting the secondary pion production by 5 GeV proton to the laser target, and again simulated with the Bettini cascade models. So here showing is for example, there is a sort of quite changes in for the cases of proton. but it's not nearly sensitive to the pion production. But the point is now current default is 0, so it's basically this is a turn off in principle. But here showing is probably the better value is you're moving the Butini trailing radius to the new point here, so suggesting 0.7. Then you do relevant actually test, but the thing's getting more complicated because in the previous plot it shows maybe the new the better parameter is 0.7. So here comparing still the secondary particle production for proton and the pion for two different cases. So the blue and the green is for the case comparing the proton, secondary proton production for the default value versus new value. So rather this you cannot come up with a single point, right, to give us the best for this case is Butini radius scale. So you can ask, okay, I can combine all these maybe chi-square and come up with sort of the one the combined chi-square, then set the default value. But that's also probably not the case because now there are more and more it's actually dependent parameters that comes into the analysis. For example, here is the different cases. The message here is for example, right now the FDF, the nuclear hydronuclear interaction, for example, probability of involving nuclear into the cascade is given by this. And then, so this is basically the probability is expressed as the sort of Gaussian times the constant. This constant time is many physical parameters. And right now, this P1 is actually fixed value. But the study shows there is a strong A dependency. So until you take into account all this in the overall integrated analysis, it's very hard to actually come up with the best set of the parameter you can actually set as a default. So, but there is the lucky cases also. So this is the production of hadron 458 GeV proton beam interacting with the carbon targets and with the pretty open models. So for these cases, all these secondary the particle production basically follow same trend. So the current default is 0.3, but you can easily move this to the 0.1 without actually conflict between the trend. And so, but this is a kind of a very rare case. So the Geant4 collaboration basically they developed, try to understand all this, the complexity first, then you open up to some the possibility the end user can do the uncertainty or the impact of the physics model to directly to the physics observables. So still this is the developing work, and so the primary goal is the understanding first, basically error and the correlation between different physics models. And also as I mentioned, this is basically the many different combination of the different cases because you have to consider a wide range of energies and the different particles and the different material and the different production mechanisms. So the choice to do all these multiple the analysis by now is using the proposed tool is the professor. But not necessarily this will be the fixed, I think, the candidate, but they can accommodate the other available tool out there. But this professor is, I think, known to be quite a long time in the HEP community, and try to mitigate the sort of computing requirement, also the brutal, for example, the tuning process and so on. So it's a random sampling basis in n parameter space, and the field-wise interpolation is a Monte Carlo result to the second or third order polynomial, and the cost value is basically something similar to chi-square type of the quantity and minimized in the numerical way. And so the more I think the result they will collect this type of things, then they try to actually use a professor to come up with the better set of the parameters for starting with the hard-learning models. So summary, in response to requests from the Geant4 user community, the Geant4 developer are developing a software toolkit to explore impact of varying Geant4 model parameter on simulation result. And toolkit has been used for first cases for the Geant4 hard-learning model. In this case, is Pertini FTF Pertini cascade. And the early the result has been shown in a couple of cases, and also the next step is the based on this collected study, and they will try to do more global analysis using professor. And last but not least, this is sort of the recommendation from Geant4 hard-learning group, and saying the message is don't try to retune blindly, because now you can do with the machine learning, and they can come up with the sort of, they can handle many parameters at the same time. But just talk to, I think, the developer first, so try to have a mutual feedback to actually understand what the impact of the variation physics model directly to in the physics data.
Yeah, I just wanted to make a remark that seems a bit contradictory, because you've shown this nice tool and then say don't use it. but I just wanted to clarify this, because in Geant4 we're going through this over and over again, that if you improve Geant4 on the available tuning data, then it's not clear whether you had an improvement or not. And the reason is that, unfortunately, for organic physics, the available data on which we tune Geant4 are too few, because there are too few data, are too few. So I mean, when you improve even on this data, you're not sure that you're really improving for the experiment. So the warning is for that. But the tool would work very well if we had enough spin target and then spin data. That would be perfect. The point is that we don't have enough. There's not enough in the data.
Yeah, I think it would be interesting to talk some with the machine learning group, because, of course, these issues, you use different language, but the concepts are largely the same. The too few data has to do with like an overfitting problem and things. Also, this professor tool tuning, which is used a lot for like tuning Pythia and things, you know, it's an okay tool that makes lots of simplifying assumptions, basically make it numerically tractable. But recently, in the last year or so, there have been a lot of more sophisticated, much more efficient optimization algorithms that are, you know, Bayesian optimization techniques and things that I think will be probably nicer than professor. They've been used in the context of things like Pythia, and they work efficiently, and they make many fewer assumptions. So, but this is a very important project. But I think it would be interesting to maybe connect with some of the machine learning groups that are going on.
So how heavy are your jobs? So to run this entire workflow from parameter settings to all the way to chi-square, how long does that take?
It depends on the computing actually clock. So typically, the Julia usually when the reference release each month, she usually runs like 2 days and come up with the fault validation and put it in the database first. Then also this is a sort of a decoupled with that, but usually she's using same cluster. So they so depend. For example, the clusters Julia using is we have something like the 36 AMD 32 core plus 24 the 12 core internal team. So basically she uses all of them to.
So one parameter setting, so I imagine you submit all the different settings at the same time, and one takes 2 days?
Well, you can do configure things many different ways. But is usually the more controllable test is the single interaction test, right? Which doesn't require actually the computing. So, but because you have to learn many of these and combine this set actually with aggregate. But you can, I think all this is basically the frame of the workflow, and you can parallelize it as many as you could. So especially the art framework is the multi-threading.
Yeah. One other thing that would be interesting to think about is once this matures, how you would communicate the sort of different sets of parameter settings that are compatible with the data, the kind of uncertainty model, right? I mean, you have a best default, but then you're going to have several other settings that are somehow like, chi-square 1 or something like that, right? And it seems a little bit like the neural net PDF kind of efforts, where they have somehow you send a whole bunch of different settings with some weights or something like that. But there will be a whole issue about how to communicate, like, if this tool evolves and is nice, how it gets propagated back to like the experiment, so they can try to assess these systematics like you're talking about. Yeah. Okay. Any other questions? Okay. Thanks. So good. Thanks, sir.